Good morning, fine folks. This lecture is to be a rehashing and a bringing together of the topics discussed and introduced at the end of last week and beginning today and for the rest of this week. At this point in chemistry, you can't separate the fundamental structure of the atoms and periodic table from the lessons of how chemical reactions and chemical bonding occurs. And so we begin the malevolent and benevolent phenomena of chemical bonding. I've given you a PowerPoint that I did not lecture on last week. And then the week before that, I gave a lecture that I did give you the PowerPoint for on chemical reactions as an introduction to these next 2 weeks. This is the second of those 2 weeks I introduced 2 weeks almost ago. So to get down to it, chemical bonding. Nothing will be said in here about isotopes because by the time you're watching this, you ought to have covered isotopes, read and know that isotopes do not influence chemical reactions. They are simply heavier or lighter, and really, whose identity is changed by their weight? Shouldn't be, and neither is an atom. But these two concepts right here dictate everything about chemical bonding, okay? And that's what we're going to go through. So this really needs no real deep lecture because you've done the readings, and the next reading will reinforce this. But we're going to go ahead and go on. If you don't know yet what valence electrons are or the octet rule on ions, you need to go back to past lectures and introductions to see those definitions. But I will review them as we go through this. Now, so chemical bonds, that is an attraction between two or more atoms. This is everything in the universe, from this flower bed to the books that you read to the pots and pans in your kitchen. All those materials that we can touch and feel and see are only there because, obviously, many atoms of various elements make them up. So how did that happen? Why did that happen? Well, there's an attraction between two or more atoms. What causes that attraction is the topic of this week and next week. The interaction between valence electrons. That's the answer in its most reduced form. At the very nature of all materials that you can experience, including your own body, it is the interaction between valence electrons. So you remember the analogy I gave? If you were to blow up a bumblebee or a pea to be the size, the nucleus of an atom to be the size of a bumblebee or a pea, put it in the middle of a football field, and those first electrons would be on the outer edge of the parking lot. And that's just that first ring that only holds 2 electrons, right? Then the next one held 8, and then the one even further out held 8. So you're talking about miles apart at something that's pea size. So those are the valence electrons, the outermost electrons, as we satisfy the octet rule. So no 2 nuclei will ever hardly come into any contact. This sort of thing only happens, for those of you who took earth science, only happens in star formation, only happens in space under high pressure and gravity. If we could get 2 nuclei to fuse, you'd have the power of the sun in the palm of your hand. That's the substance of Spider-Man 2. If you remember, he needed more tritium. Not Spider-Man. Who was it? That other guy. So, who? Doc Ock. So, nuclear fusion just doesn't occur. You need too much force. There are particle colliders on Earth, 2 of them at least, that attempt to do this, and they get them at high speeds. But my point is that when any 2 atoms even come close to each other, the first things that are going to interact are those outermost levels of electrons, right? And then further in are the middle to the nucleus. So the interaction between valence electrons determines, okay, the chemical bond. They can be ionic bonds or covalent bonds, depending on where they sit in accordance with the octet rule, okay? So we're getting into ionic bonds and covalent bonds after this lecture, and starting Tuesday and Wednesday, we're segging into it. All right, so the octet rule states that an octet in the outer shell makes atoms stable or happy. An oct refers to 8. So electrons are lost, gained, or shared to form that octet. Doesn't matter if they lose them, doesn't matter to them if they gain them, doesn't matter if it's shared. As long as they can get them at whatever cost, they will be happy and stable if they can satisfy that octet rule. I guess I could draw you a quick memory here. So when we said octet rule, what we're referring to is the shell. The shell. And remember, there's 1, 2, 3, 4 shells. And then we had the number of electrons that the shell can hold. Electrons, right? And the number of electrons that that shell could hold in the first one was 2, and then 8, 8, 8. All right, remember that? So that's just kind of refresh your memory if you didn't. But elements want to be like their closest noble gas. I'm probably not going to go too much into that, although it's true. Oops, how do I? So because we are interested in the outermost valence shell, that is, while we've learned the Bohr model, and we know now that the periods represent how many shells go around and how many, here we are. So first period, they have 1 shell around them. Second period has 2 shells. Third period has 3 shells, and so forth, right? If this is the nucleus, nucleus, nucleus. Okay. Whereas each of the groups have 1 electron in their outermost shell, 2 electrons in their outermost shell, skip a few, 3 electrons, 4, 5, 6, 7, and 8 electrons. Now you'll notice that this group over here, 8, those are the noble gases. And so 8 happens to be lined up in this group here. And this is called the electron dot structure. And this is a summarized view of everything we've learned. So it's really powerful. It says a whole lot with very little. Okay. The rest of it, you just kind of have to keep in the back of your mind. But again, because mass number of neutrons, protons, all that, we're not messing with. What we're talking about when we're talking about chemical bonds in chemistry now are the valence electrons, and do they satisfy the octet rule? Those are the only 2 things we're interested in. So everything I just said should be a review. You ready? So 1 electron, and how many dots do each of these elements have around them? You can see. Second group, how many dots do they have? Correct. Third, 1, 2, 3. Fourth, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, when you look at this, and you're going to have to pause this video for a bit to look at this, but I want you to pick up on some patterns. So pause it and look. Okay, so what you notice that over here, the blue, we have metals, and over here, the yellows, we have the non-metals. So the left-hand side are metals. They tend to release electrons. The non-metals that are yellow tend to take those electrons. So any 2 elements from opposite sides of the periodic table are going to react very well and very quickly with each other, because each side or one side needs what the other side has. Okay, you also look here and you can see a pattern in how the electrons are placed. So the first electron, we represent the red dot on the right-hand side, and the next one we go right to the opposite. So you see how beryllium has it, 1 on the right, 1 on the left. Go to boron, and we go to the top. And then carbon, we go down to the bottom. So you have this crisscross. I'm going to put a generic A right here for some atom, and it goes 1, 2, 3, 4. Now each side has 1 electron. Then we go back up to the top, 5. And you look at oxygen, we go over here, 6. Fluorine, 7, and the last one to be filled is this one, 8. Okay, did y'all see that? One more time. If we have some generic atom, let's just say neon actually, because neon is a noble gas. And we're going to draw neon over here. This is neon 10. So the order in which those electrons were placed were 1, 2, 3, 4, 5, 6, 7, 8. So the first one gets placed here, but then from that point you can see the pattern. We go to the top, side, bottom, top, side, bottom. All right, and then this is the last one. It goes all the way around. And then, does that make sense? Okay, let me clear that. Because this is a lot easier to write, right? I mean, if you looked at the rest of what we've been doing with the Bohr models, you have the nucleus, you have the protons, the shells, the electron numbers, and it's been getting confusing. And we're not totally done with those yet because they do help our understanding. But right here, I just want to introduce the electron dot structure, okay? So if I were to just do a quick example of something you'll be seeing and how we use this, let's draw a lithium. So Li, and it has 1 valence electron. Now let's look at one over here, fluorine, F. Let's put their valence or dot structure. We have 1, 2, 3, 4, 5, 6, 7. We can see clearly that we're missing 1 right there. And we also see clearly that lithium has 1 right there. So what's going to happen when these two interact? So this electron will want to come over here, fill this, and now fluorine will have all 8, 2, 4, 6, 8, and satisfies the octet rule. Lithium will then not have that one there, but what happens is it falls to being a helium. So lithium is atomic number 3. Look at helium is atomic number 2. So lithium having only 1 shell now, because that electron left, will look just like helium, and it'll have those 2. And having 1 shell, as you know, you have to remember the octet rule. The first shell holds how many electrons? 2. And so now lithium is stable. But we do got to add something here. We have to add the charges they inherited. So lithium, having lost that electron over here, right, now becomes a positive 1, just as we've learned about ions, and you'll learn some more after this lecture, depending on which order you do it. And fluorine, having gained the electron, becomes a negative. So we have a positive lithium and a negative fluorine. And guess what that is? Whoops, chihuahuas. I messed that one up. Negative fluorine, not positive fluorine. And so a negative lithium and a positive lithium and a negative fluorine makes, I'm going to draw it over here, lithium fluoride. And that's a medication. That's actually the active ingredient in medication for bipolar. It's lithium fluoride. So very useful. Very, I mean, lithium has nothing to do, and fluorine have nothing to do with each other. Fluorine's pretty deadly, actually. But you put these two together and you get something that is fine, lithium fluoride, and makes up a medication. Okay, so what you've seen is that with lithium fluoride is what you call an ionic bond. And why is it an ion? Because we had a positively charged lithium and a negatively charged fluorine. Each of those are ions, charged particles. So ionic compounds result when a metal like lithium reacts with a nonmetal, such as fluorine. So metal plus a nonmetal equals an ionic bond. Must memorize that. Metals lose the electron to match the number of valence electrons to their nearest noble gas. We saw that with lithium. Lithium, atomic number 3, wanted to become like helium, atomic number 2. It's the closest one to it. Metals become positive ions, and so positive, we say cations. I think of the T in cations as a positive sign. So that might help you remember that cations are the positive ions. And that's what happens when you lose a negative charge. You become positive. Positive ions form when the number of electrons are less than the number of protons. And again, a principle you have to remember is that proton number doesn't change. The moment you change the proton, you're changing the element we're talking about, and that doesn't do any good. So within, say, carbon or hydrogen or oxygen, to continue talking about carbon or hydrogen or oxygen, we have to assume, of course, that the proton number is the same. Otherwise, it would not be carbon, hydrogen, or oxygen. Okay, so the proton number remains the same. What can change? The electron number. Why? To satisfy the octet rule. It says it wants 8. And what's it going to do? Anything it needs to gain, lose, or share electrons in order to become stable or satisfy the octet rule. A side effect of that is that you inherit a charge. You will be either positive or negative, depending on which of those circumstances it was. So nonmetals gain electrons to match the number of valence electrons in their nearest noble gas. So that's all the way on the right-hand side of the periodic table now. And these guys will gain. Nonmetals become negative ions, or what we call anions. The letter A, or the term an means lacking or without. So you're saying without ions or negative ions. Negative ions form when the number of electrons are more than the number of protons. And the perfect example is that of sodium chloride. Okay, and I think we've seen this example before. We'll look at it one last time. So we have to, there we go. So we have to draw the Bohr model, and we can do this with the dot structures as well. Actually, let's do it both ways. So let's first use the electron dot structure we just learned. So sodium, when you look at your periodic table, is in which group? First group. Therefore, has 1 electron. And we have chlorine. Find chlorine. Its atomic number should be 17. So there's Cl, chlorine. And it's in which group? 1, 2, 3. You should look at it. It'll be in group 7. So let's put our 7 electrons, the valence ones, because that's all we're concerned with. So 1, 2, 3, 4, 5, 6, 7. So there's 7 electrons. And we are missing that 8th one. Under sodium, we're missing a whole slew of them, right? We need 7 more. And that's not going to happen. You can see what happens is that this electron can easily fill up chlorine's spot, and then we have nothing here. So what happens as a result of that? We inherit a charge. So sodium now becomes sodium positive. It lost a negative charge, and chlorine becomes chlorine negative because it gained that electron. And once again, this is an equal and opposite attraction, a positive cation and a negative anion, and you have sodium chlorine. This is crazy. Do this. Go YouTube real quick. You can find 2-minute videos, 1-minute videos on sodium in water. Just type in sodium in water and see what happens. Go. Welcome back. Now, chlorine. What do y'all know about chlorine? Where do y'all see chlorine? Where do you hear chlorine? Swimming pools. That's right. Bathroom cleaner, maybe. Bathroom cleaner. Clorox is chlorine. You know, city municipalities use chlorine gas to kill germs chemically before they release the water to homes. Swimming pools, why do we have chlorinated water? Kill germs, keep it clean, keep things from growing. Chlorine is anti-life. Bathrooms, same thing. We use it to kind of kill the mold, right? So sodium, with its 11 protons, and we got our 2 electrons, 8 electrons makes 10, so we need our 1 more, a third shell, 1 electron. Chlorine, with 17 protons, has 2 in the innermost. Y'all should be getting used to these diagrams now. 8 So 8, 10, we need how many? 7 more. So protons equals electrons, yes. Oops, that's a plus sign. Protons equals electrons, yes. Are they stable? No. So what's going to happen here? As we just saw, this electron, that one's going to fall over there, and the 7 becomes an 8. And so chlorine is now stable, but with an extra electron, chlorine becomes negative. And sodium, having lost the electron, 11 positive, 10 negative, means sodium is positive. So you've Googled by now, hopefully, sodium in water and what happens. Ooh, if you didn't do it, I'm not going to tell you. So you can imagine that. You know, you don't want that in your body. They used to do this in science chemistry labs, and there's always one mischievous one who'll throw it down the drain and set off the fire alarms. Ooh. I'm going to erase all this because this is all we're really interested in. Ions. We have 2 ions. But you know, you put sodium and chlorine together, 2 deadly items, and all of a sudden you have something that emerges that is more than either one of those in and of themselves. Sodium chloride. Oh, can you pass the salt, please? Sodium chloride is salt. Of course, nations have gone to war over this in the past, far past, but it was a hot commodity. Salt lakes. So chlorine kills life, steals electrons. Sodium explodes in water. But you put the 2 together, and all of a sudden you have something called electrolytes and salt, which your body needs much of. So that's crazy. We call that an emergent property for life. And this is the way chemistry is going to unfold. You're going to have atoms and elements that have their own unique properties and characteristics that will cause them to bind in a certain way to other elements. But the moment they bind to other elements, everything changes. And so that's what makes the study of chemistry so unique and exciting. Okay, so that's ionic bonding in a nutshell. Covalent bonding I'm not going to talk about right now, but I do want to just define it for you. This is going to be the topic of next week. A non-metal plus a non-metal. So you're talking about 2 elements from the same side of the periodic table, and that's going to be anything from the right-hand side bonding with something else from the right-hand side of the periodic table. So covalent bonds result when non-metals react. They share electrons to achieve the octet. There's no transfer, there's no give and take, it's just sharing. So we'll get to more of that later. So these last few slides, there's nothing much I want to talk about. I want you to pop quiz yourself. So reviewing metals and non-metals, classify each element as a metal or non-metal by dragging each element to the correct category. I'm not posting this as your PowerPoint, so you can't do it, but I want you to look up hydrogen, cesium, phosphorus, lithium, nitrogen, boron, and where would you put it? Would you put it on the metal side, or is it on the non-metal side? Just look at your periodic table. All right. Ionic bonds or covalent bonds? Okay, here's your answer choices. Electrons are shared. Is that an ionic bond or covalent bond? 2 nonmetals combine. Is that an ionic bond or covalent bond? All right, you ready? Electrons are shared in covalent bonds. 2 nonmetals, that comes from, let's see, nonmetals on the right-hand side, there's 2 of them, also covalent bond. Each element has a charge. Opposite charges attract. Charged atoms are ions, therefore, when they attract, that's an ionic bond. A metal and a non-metal combine. That's 2 different sides of the periodic table. That's going to be ionic bonds. Electrons are transferred. Okay, they're not being shared. We saw that sharing was covalent, so this must be ionic bonds. All right, and there's a quick review what we've done in this lecture. Hopefully this makes a little more sense to chemical bonding, and we'll see you again soon.